Hello everyone, welcome to Statistical Foundation for Big Data Analysis. Today in this class we will discuss basics of hypothesis testing. We will continuing with our module 3, which is the second module on statistical inference. So far we have discussed point estimation and interval estimation. Now we are moving to a altogether different philosophy regarding inference. So statistical inference generally, as we saw repeatedly, is of two kinds. So, but statistical inference itself is basically about taking decisions about population based on a sample. Population is unknown, sample is known. You collect sample out of population and you basically derive decision about the population based on that sample. This is what the framework of statistical inference. Now, statistical inference is of two kinds. We discussed hypothesis testing and estimation. For estimation, we have so far discussed estimation, where basically you are trying to guess a particular value. In case of hypothesis testing, you do something slightly different. So, let us compare the different kinds of questions. So, suppose the first question is, what is the average height of a person living in Antarctica? And second question too, what is the average height of a person in India? So, what is the average height of a person living in India above 7 feet? So, now if you take all people in India whose height is above 7 feet, what is the average height of those people? Now, the point is that we probably do not know anything about the average height of a person in Antarctica. So, when you have this kind of situation where to begin with you have no idea, you collect the sample and whatever the sample is giving you, you take it. Suppose you, let us say, just to give you an example, you picked up two people from Antarctica, one has height 5 feet 8 inch, another person has 5 feet 10 inch. You just take the average, 5 feet 9 inch is your guess. This is the type of problem, this is the approach of statistical inference, in which this kind of statistical inference, which is point estimation, where you are basically trying to predict a particular, you are trying to basically, you are giving a value. Well, that can be a fixed value or you can say interval, which we saw in case of interval estimation, but here most importantly you are supplying a value for the parameter. So, as an outcome of your inference, you are supplying a value for the parameter. That is what your hypothesis, that is what your estimation does. Now, in case of hypothesis testing, the situation is slightly different. This is not the situation where you have no idea. For example, you know that there are very few people in India whose height is above 7 feet. So, you have some idea about this. This is a situation where you have some idea about the answer. Now, suppose you collected a sample which is confirms your idea, then well and good, you actually know that what idea you had, you collected the sample that supports the idea, you move on. Now, suppose you collect a sample which is actually giving you something drastically different from your existing idea, what will you do? This is the scenario of hypothesis testing. Just to give another example, suppose what you have the idea, what is the average temperature on the surface of Neptune on January 26, 2026. You have no idea, right? You have no idea what you can do. I mean, you do not really know about Neptune, perhaps you do not have a way to measure it. You will do a sample, let us say you will use some satellite images or so on, targeted to that on January 26 on next particular area in the surface of Neptune. Maybe you will collect data from 100 sources or 10 sources, whatever you have access to, and then you take the average of that or some other function of that, let us say the median of that or whatever, most frequently appearing number of that or whatever, depends on the scale you are measuring, and that is the best you can do. It has advantages, it has disadvantages. Now, the point is, if the question is what is the average temperature in Calcutta on July 24, 2026, what is the average? So suppose the question is that is the average temperature in Kolkata on July 24, 2026 is above 18 degrees Celsius or not? If your question is that, let's say you collect data from, so suppose let's say you ask one person to collect the data, and the person collects the data, the average temperature in Calcutta on that day is 5 degrees Celsius. You just don't, even if it's like, let's say that you have collected data from 5 sources or 10 sources and the average temperature comes out to be 5 degrees Celsius on July 24, 2026, you really don't stop there, because this is some completely counterintuitive, because on July 24, in the month of July, practically never the temperature is 5 degrees Celsius in Calcutta. So if the average temperature comes out, the answer to the data collection gives you something like this. You have some basis, some a priori knowledge with respect to which you can compare it and decide in favor of or against it. Like, there can be a sample collection error, there can be some miscommunication, but the point is you have a basis and existing wisdom with respect to which you can check the result of your sample collection. In case of inference, in case of estimation, you do not have any such thing. That is the fundamental difference between hypothesis testing and estimation. In case of hypothesis testing, you have collected the data. Based on the data, you are coming up with some conclusion. Sure, here also you are doing, but that conclusion is not your primary object. In case of estimation, you collected data, come up with some conclusion, and that's it, move on with that. In case of hypothesis testing, you come up with a conclusion only to confirm or deny with respect to something existing. I know it's little vague, I'll make it more rigorous, but the point, the fundamental difference between hypothesis testing and estimation is that in case of hypothesis testing, there is an existing wisdom with respect to which you want to test the collected data, or with respect to the collected data, you want to test the validity of the existing wisdom. Just like here, if the question was, is the average height of a person living in India above 7 feet or not, if the data you have collected and it comes out indeed to be above 7 feet, that looks suspicious to you, because you know your standard answer to this question is no, because you have some idea about the height of an average Indian person. Even if you don't, you kind of know that not that tall. So if you have collected sample, if the answer is coming out to be that, then you have a reason to believe that there is something wrong with the sample, or there is something drastically wrong with your understanding of the heights of Indians. But nevertheless, there is something behind which has to be utilized in one way or other. Some knowledge, some wisdom is there which has to be utilized in the inference. Here, there is no such thing. Just to give another example, so what is the average score of students in a national level mathematics exam? Compare this with the question, do students score more than 95% on an average in a national level mathematics exam? This is highly unlikely scenario. However, for this one, you really do not have much idea. So here, you collect the data, whatever the data tells you, do something, use some theory to come up with a good prediction based on the data, but whatever the data tells you, that's it. Here, if your data shows on an average students are scoring 99% in a national level mathematics exam, that looks suspicious. You have some existing understanding of the score of an average mathematical aptitude of a population. So you can test the validity either of your data collection or your method of inference, or the existing wisdom. Either you can validate, test the validity of the existing wisdom based on your data. Maybe students have gone really good. Maybe that's one year where you had exceptionally good students sitting for the exam. So your inference that the average performance has to be not, definitely not above 95%, that wisdom is wrong, or there is something suspicious about the data. So, this is what this question 2's in these 3 examples are. They lead you to something called hypothesis testing, another big approach to statistical inference. So, in case of more formally, so for a statistical test, what you will do is the following. There will be an existing assertion about a population and there will be an alternative given to you. They are not in the symmetric footing. The existing assertion is the classical wisdom, conventional wisdom, status quo. The alternative is something that is challenging that status quo. Test will be a rule where you evaluate an assertion about a population against this alternative based on a collected sample. This assertion and the alternative statements are hypotheses of the test. Evaluation is done based on the numerical function of the sample, just like in case of estimation. You have collected a sample, you calculate a statistic out of it, that is a numerical value of this. Based on that you come up with a decision, but unlike estimation, here the decision is not, let us say, predict a particular value or predict an interval where the particular value of the parameter belongs to. Here what you do, you test 2 statements about population. In many cases the statements are about the population parameters, but nevertheless you test 2 statements, and one of the statement generally has this status of status quo, conventional wisdom, conventional thing to go about. Wisdom, well, this is really reduces the case to knowledge. I mean, that is how the examples were framed, existing knowledge, but there are other cases also. There will be other examples where I will just immediately demonstrate. There are other reasons, not conventional wisdom, but there are other reasons to treat something as status quo, because hypothesis testing tends to address situation where two of the statements are not in the same footing. So, what is generally when you are doing with testing between conventional wisdom and alternate? So, when you are choosing between a conventional wisdom and a new alternative, what is the situation you face? So, if you are a safe person, you will go with the conventional wisdom, and there is something to be said in favor of being a safe person. You are going with conventional wisdom means you are not taking a chance. At worst, you are missing a new opportunity, but nevertheless something is conventional wisdom means going with that will keep the life going. If you pick the alternative wrongly, you may get into a disaster, because conventional wisdom is something saying that this is nice to do this. This is right, traditionally it is believed. If you wrongly pick up the assertion, new assertion is something that is coming up with it as a challenge. On many occasions that can be just a wishful thinking. So, if you dump the conventional wisdom in favor of wishful thinking, you are basically going against the tide, going against something which has been established by certain, something is conventional wisdom, meaning there is some reason behind it. You are going against that reason. If you dump the alternate conventional wisdom wrongly. So, in particular, this is a situation which is at best, the choice is between, so the errors of, there are 2 kinds of errors. You can wrongly reject the conventional wisdom and go with the alternative. There you are simply ignoring the knowledge and wisdom that has been status quo and getting into trouble. And the other side is simply you are missing an opportunity. So, if you are a safer person, missing an opportunity perhaps is less, bad than wrongly ignoring the conventional wisdom. And this is not just about personal experiences or personal choices. One may say that you cannot gain without taking a risk, but sometimes taking risk can be disastrous. Just to show you with an example. So there are two kinds of errors that we were discussing. So suppose the decision is reject the assertion versus reject the alternate, and reality is the assertion is true, assertion is false. So if the assertion is true and you reject the assertion, you get a particular type of error, which is the wrongly rejecting the assertion. And if the assertion is false and you reject the assertion, you get no error. If the assertion is true, you reject the alternate, that is, you stay with the assertion, then there is no error. If assertion is false and you reject the alternate, you lead to certain error. The more serious error is the type 1 error, namely rejecting the assertion when assertion is true, because there you are going against the conventional wisdom. So the point is that what will be the conventional wisdom and what will be your assertion depends on what you are trying to protect more. And the next example, which is a bit morbid, will make it clear that it's not really a matter of taking risk and taking a risk and no risk no gain kind of situation. Like if you want to do better in life, you have to take risk, that kind of situation. But hypothesis testing is not really trying to model that kind of situation. Far from it, hypothesis testing is trying to model a situation where you're basically trying to judge whether the sample, the collected data, gives you overwhelming evidence against a certain conventional wisdom or not, or certain assertion or not. Here is an example. So suppose a person goes to with a tumor, goes to a doctor checks the patient and makes a decision. Tumors can be malignant, that is, it can be cancerous, it may not be cancerous. Now doctor can make two kinds of mistake: fails to diagnose the existing cancer and tells the patient that you're fine, and wrongly diagnoses cancer at the first visit. So when it says here this can be carcinogenic, and another decision is it's not a carcinogenic. So what are the two kinds of error? When there is actually the tumor is carcinogenic, the doctor can say that it's not carcinogenic. What will that lead to? Well, the patient will be happy and not get a treatment of cancer and move on with life, and maybe it will get detected when it actually shows other symptoms in higher stages. Another thing is, another error the doctor can make, wrongly diagnose the cancer. But the point is, in case of detection, medical detection, there will, the moment, even if the doctor thinks that this is carcinogenic, they will ask the patient to do further tests, and the person will get tested, and eventually most likely the error will get rectified and the person will move on. Or even at worst, even if the person gets some treatment, it's probably better, so wrongly gets some medication, it will probably better than actually not getting any treatment for a cancer, for an existing cancer. So obviously here the more serious error is the failing to diagnose existing cancer. So this will be our type 1 error. So our assertion, the one we will try to protect, will be the patient has cancer, and the alternate will be the patient does not have cancer. So our conventional wisdom in this case, that is the direction where we would like to play safe, is that assume the patient has cancer and do further tests, because the error of rejecting this wrongly is far more serious. That is, error of rejecting this assertion that the patient has cancer wrongly is far more serious error than rejecting the than the other error, namely detecting the cancer wrongly, because that will anyway have further buffers. So, this brings us to the mathematical framework again. So, this takes us to this notion of type 1 error and type 2 error. So, you have you have an assertion and an alternate. So, if the assertion is true and you have rejected assertion, you make one kind of error, and if the assertion is false and you reject the alternate, then you also make another kind of error. The two statements that you are comparing, amongst which you will call, one you will call assertion, the one which has this property that rejecting this one when it is true falsely has the error that is committed by rejecting this one falsely is far more serious. That is called type 1 error, and the one whose truth you are rejecting wrongly to get type 1 error is called null hypothesis, and the other one is called alternate hypothesis. So, from the situation, from the one you are trying to protect, from the situation, from the problem you are trying to solve, from the situation it will be clear which one is more serious error and which one is less serious error, and that will determine which one is your type 1 error and which one is type 2 error, and as a consequence that will determine which one is the null hypothesis, which one is the alternate hypothesis. So, job of the hypothesis testing is to decide there are overwhelming evidence to reject null hypothesis. If there aren't overwhelming evidence, this is the going along with this is the safe thing to do, and you do that. So, objective for this is to test whether there is an overwhelming evidence to reject a hypothesis H0 null hypothesis in favor of a stated alternate H1 based on the sample. Choose a numerical function t of the observables such that one can predict the behavior of t under null hypothesis and alternate hypothesis. So, basically what happens is that you just assume the null hypothesis is true. So, when null hypothesis is true, that make some statement about the underlying probability distribution of the population, and based on that information about the probability distribution of the population, you get some understanding of the sample statistics. So, you kind of say that sample statistic behaving like this under the null hypothesis has high probability or low probability. So, basically if under null hypothesis, when the null hypothesis is true, if you assume the null hypothesis is true, but you are observing the sample statistic is getting some value which is very unlikely under null hypothesis, then you judge how unlikely it is. If it is extremely unlikely, then only you reject the null hypothesis in favor of alternate, only if it is more likely to take that value under the alternate. So, basically the goal will be to choose a critical region or a rejection region such that if the value is in this region, the observations are overwhelmingly more likely to come from H1 than H0. So, type 1 error and type 2 error. Type 1 error is when H0, the null hypothesis is true and the value is inside the critical region, that is wrongly rejecting the null hypothesis is called type 1 error, and type 2 error is when H1 is true and the value is not inside the critical region, that is the wrongly accepting the null hypothesis, or wrongly not rejecting the null hypothesis. Basically H0 true, reject H0 type 1 error, H0 false, do not reject H0 type 2 error. So, just to give you an example, let us get back to this coin tossing example. Suppose a coin is tossed and the probability of getting head is p. You want to test between H0 p equal to 0.5 and H1. Sorry, there is a typo, it should be p equal to 0.6. I just miswrote there. I will just correct it. It should be p equal to 0.6. H0 p equal to 0.5 and H1 p equal to 0.6. H0 is rejected in favor of H1. If suppose the rule is that H0 is rejected in favor of H1 based on outcomes of 10 tosses of the coin. Suppose if at least 7 heads were observed, H0 is rejected. Suppose this is the rule. So, we were mentioning that you come up with a rule. So, you have a sample, you come up with a rule such that based on this, if this belongs to a certain region, you will reject H0, otherwise you will not reject H0. Suppose your rule is that H0 is rejected in favor of H1 based on the outcomes of 10 tosses of the coin if at least 7 heads were observed. Now observe that this is sort of makes intuitive sense, in a sense, like to do something like this, because if head probability is more, then it is more likely that you will get more heads. But the point is, how more is enough? 0.5 and 0.6 are not that far. So, the probability of getting at least 7 head under 0.6 is more, but that can happen. It is still probabilistic situation. It can still, you can get 7 heads or more under p equal to 0.5. Now, if your p equal to 0.5 is the status quo, just based on some sample, you do not, even if shows certain aberration, you do not want to reject it right away. So, in particular, it is important to see the type 1 error and type 2 errors. So, if this is your rule, that is, you reject H0 in favor of H1 based on 10 tosses and you get at least 7 heads, what is the type 1 error and what is the type 2 error? Number of head here is x. As you can see, you are counting the number of heads out of 10 toss, and head probability, suppose it is p. So, this is binomial 10p. What is type 1 error? Probability of rejecting null hypothesis p equal to 0.5 when p actually the probability is p equal to 0.5, that is when binomial, it is binomial 10 0.5, what is the probability of getting x bigger than equal to 7? You can calculate that here it is 0.172. And what is the type 2 error? Well, when p equal to 0.6, that is indeed the null hypothesis is not true, the alternate is true, the probability of actually accepting the null hypothesis, you can see from binomial probability, here you have to calculate probability x less than 7 for binomial 10p. So, you can do that, you can calculate probability of x equal to 7, x equal to 8, x equal to 9 and x equal to 10 and divide it and subtract it from 1. So, it will give you type 2 error is 0.618. Note that type 1 error is still fairly smaller, the probability of getting type 1 error is fairly small, but probability of getting type 2 error is more than 50%. Although you want the type 1 error is more serious, of course. So, you want to protect type 1 error, but you want the type 2 error also to be very little, and also in this inference model one may say even 0.17 is fairly big for type 1 error. So, what you have to do, you have to design a different test or do something else. So, in fact, one can carefully check that for this kind of sample, that if your rule is that your x is, you reject it when x greater than equal to 7, the probability of type 1 error is 0.171 and here type 2 error is 0.61. If it is greater than equal to 6, then it is 0.37 and 0.36. If it is greater than equal to 8, it is 0.054 and 0.83. Now, notice, compare 7 and 8. What really you are doing? You are rejecting when x is bigger than equal to 8, that is, you are even more protecting this one. So, more you protect the null hypothesis, the type 1 error keeps going down, because for less smaller region you are rejecting the null hypothesis. Null hypothesis is more, it's almost sacrosanct. The rejecting null hypothesis for 7 or more heads is definitely a bigger set than rejecting null hypothesis when it is 8 or more. So, the second one definitely should have less type 1 error, that is less probability of rejecting null hypothesis wrongly. So, that is clear here, this is less than this. For 6 it is of course more. So, you can see that the bigger this value goes, type 1 error keeps going up. But then there is a giveaway. If you try to protect null hypothesis too much, you end up increasing the probability of type 2 error, which is clear here. So, quickly, just to wrap up this discussion, you want a test where both null hypothesis and alternate hypothesis are protected. Null hypothesis and alternate, so you want a test where both type 1 error and type 2 error are, both of them are less. So, the only way to do it is to increase the sample size. So, roughly speaking, if you want to avoid both kinds of error, if you want to reduce both kind of error, basically what you have to do, you have to collect more samples. So, I will get into this in more details. So, for sample size 100, you can see that you are achieving, so for sample size 100, you are achieving very little type 1 error, you are achieving very little type 1 error at 70, whereas here to get that amount of type 1 error, you have to already get all heads, and still type 2 error is fairly high. However, if you take 1000 size sample, you can reduce type 1 error, type 2 error both to be fairly less. So, this dynamics of reducing both type 1 error and type 2 error involves collecting more sample. I stop the talk here today. I will pick up from here tomorrow. Thank you.